Okay, so let's see how many people will survive till the end of the second journey. Remember, these are independent journeys. So what I'm allowed to do is to go back. And I'm going back to our dear friend Pythagoras. Remember, we left him a while back in the south of Italy. And eventually he gets killed, but the order, the Pythagoreans, survive. So they spread through the south of Italy. There are at least a couple of cities where they have fairly sort of strong political power, and they keep their studies. So they start to developing more and more of their mathematics, and they clearly start writing textbooks, right? They try to put things in order. So we will sort of talk a little bit more about specific, that's my device, sorry, about specific remnants of their textbook. None of them survive, but several of them later on are merged into existing textbooks, mostly Euclid. So again, let us restate their fundamental premise, something with which they sort of start. For them, mathematics is not a science of symbol manipulation. For them, mathematics is a science which describes the reality, the two fundamental aspects of our perception of the reality. Numbers, I could count chairs, and space, this continuous thing which we see in front of us. So they try, if you remember, to unify their mathematics with reducing everything to natural numbers. And in some sense, let me emphasize it again, we would say, well, they were just dreamers. Well, no, it's not. They were not dreamers. They were doing exactly what we're doing right now. We're trying to reduce everything to natural numbers, very specific natural numbers, zeros and ones. Right? So they had very similar agenda. And when they were studying all the square numbers, oblong numbers, remember this figurative, they're known as figurative numbers. They were trying to see the structure of space. In some sense, for them, the idea was that somehow you could look carefully at the space and you will see these little dots. You will see the discrete pixels. They thought that the space is somehow pixelates. And eventually you could find the discrete structure behind the continuous thing, and the reduction of space to numbers would be complete. So it's a great dream, and it's still with us. Again, this is in some sense one of the central themes of mathematics, the unifying of numbers and space. Maybe the only theme in some sense. But then a terrible catastrophe happens. So what's the catastrophe? The catastrophe is that either Pythagoras himself, as Greek historians tell us, or some of his early disciples discover that it cannot be done. There are some fundamental reasons why it cannot be done. So which sort of defeats, as it were, the whole purpose. Again, we do not, let me tell you the logic the historians of science use. They say it couldn't have been Pythagoras himself because it's too advanced. Well, I mean, what do we know? We don't know how advanced he was. So it could have been him. It could have been early Pythagoreans. Again, we have no written sources to tell us how early this thing happens. But it happens fairly early because it becomes a part of the lore. Sort of it becomes this fundamental event in the history of the Pythagoreans and in the history of science, discovery that you cannot reduce space to numbers. Let us see how they did it. Again, this is one of the ancient authorities. He tells us that Pythagoras discovered the theory of irrationals. And a very reliable source, in the sense he was a very, very great man, Proclus Diadochus. He was one of the last heads of Plato's Academy. You see, so he had this direct link to Pythagoras, as we shall see. Plato's Academy was very much influenced by Pythagoreans. So there are some evidence that it was discovered by him, but we do not know. Let us look at some fundamental idea. Sort of what they're trying to say is that at least within, let us say we have some experiment in space. And the idea is that for any given experiment, any given drawing, any given picture, you could find a unit small enough that everything will be could be discretized. So the measure doesn't actually have to be absolute. It could be relative to your problem. But for any given problem, you could find these little things in, microns, in terms of which the problem could be stated. So several definitions. So one segment is a measure of another segment. If the bigger segment could be measured by another segment, if bigger segment could be a concatenation of the smaller segments. It's a fairly simple thing. Again, how simple? Remember, eventually we will talk about it, they discovered two fundamental tools of construction. Ruler, you could draw a line, and compass. And with a compass, you could put as many of the little ones onto the big ones, so you could see if it measures it or not. Well, again, it's very simple. You say that a segment, a line segment, measures two other segments if it is a measure of both. Right? Clear. And what is the greatest measure? The greatest measure is the greatest measure. I mean, you say the greatest segment which could measure both. And very simple thing. And then what we could see, there are some very simple mathematical property of this greatest common measure. I mean, obviously, greatest common measure of of the same segment is the same segment. You could always measure 1 meter interval with 1 meter. Well, if you could measure A and B with something, say with meters, so you could measure A and A plus B with that something. Everybody agrees? I mean, again, could I use metric system? Okay. Let us say A is measurable in meters, B is measurable in meters. Therefore, A plus B will be measurable with meters. We don't need millimeters. We could do it just with meters. Then the same thing for difference. Everybody agrees? Simple rule. And, of course, greatest common measure commutes. If you could measure A and B with meters, so you could measure B and A with meters. So let us use this meter as a convenient abbreviation. So now Pythagoreans came, and it's very clear that this piece of code is the ancient Greek piece of code. You know, Egyptians had some other stuff. But that is the central piece of code for Greek mathematics. And I make a stronger claim. I claim it is the central piece of code for all of mathematics. This is how you could, if you give me two, oh, they made it. Okay, great. So when we look at two line segments, we could obviously find the greatest common measure using the following technique. First of all, we agreed that if they're equal, then we could just return one of them. Obviously, it works. Well, if one of them is less than the other, we'll just reduce the problem to a smaller one, one way or the other. And again, if you think about this beautiful procedure, is an example of an application of trichotomy law, that when we have things ordered, they're either equal, or one is greater than the other, or the other is greater than the first one. These are three choices. So we do this, and it obviously will eventually find the greatest common measure. Or will it? The question is, will it terminate? And, the gut level feeling, of course it will terminate. I mean, it will eventually get to something small enough which will measure both. Well, it doesn't quite work like that. That was this remarkable discovery which they made, that sadly enough, this thing is not an algorithm. It's a procedure. Remember, Knuth tells us that non-terminating algorithms are called procedures. They could go on forever, and this is a procedure. If it terminates, it returns a correct answer. If it doesn't terminate, there is no greatest common measure for two things. The only problem, you have to wait a while to find it out. Right? So it's a very peculiar thing. That's an example. So 196, 42, we subtract, get 154. Everybody follows? We subtract, then 112, then 70, then we have to get 28 and swap. You see now, 28 is less than 42, then we subtract 28 from 42, it becomes 14. 14 is less than 28, we subtract. Finally, we get twice 14 on both sides. We output 14 meters is the greatest common measure, right? Okay? Inches, pardon me. I didn't know about metric system. Now, again, I mentioned it before, but let us mention it again. The Greeks knew this fundamental fact about natural numbers, that any set of natural numbers has the smallest element. That is, you couldn't decrease natural numbers forever. You'll get to the smallest number, in their case 1, well, or 2. They were not quite sure whether 1 is a number. They operated with 1, but it was not quite of the same nature as 2. But eventually you get to the smallest natural number. So, therefore, they came up with this wonderful proof technique. Again, we talked about it before, is that to prove that something does not exist as a natural number, prove that if it exists, a smaller one always exists. Right? Because obviously it gives you a contradiction. So let us assume this is a little tricky bit. By the way, the proof I'm going to give you, which I firmly believe was Pythagorean proof, is a 19th century reconstruction by George Crystal. I'll show you what Greeks actually did, what survives from the Greeks, a little bit later. But many people, or most historians of Greek mathematics, actually believe that the proof which I'm going to show you was the original proof. It explains everything, if we assume that that's what they did. And it's Greek in nature. So, first of all, we assume that there is a segment which can measure a side and a diagonal for some square. Right? We could assume that. And for this given segment, we say, let's take the smallest such square. Again, obviously it exists. There should be the smallest such square. So we find a small, so in other words, if a side is measurable in inches, you say, in inches, and diagonal is measurable in inches, then the number of inches in the side and the number of inches in the diagonal are irreducible. These two numbers cannot be reduced. It couldn't be that you have 15 here and 10 here, because that would be reducible by 5. Right? So it's an irreducible quantity. It's the smallest indeed for 1 inch, we found the smallest square which could be measured both in inches, side and diagonal. Everybody follows? Okay. Now, that is our square. Okay? So there's some whole number of inches in AB. Right? There's some whole number of inches in AC. We assume. And these two numbers are irreducible. We assume you couldn't get smaller numbers. Okay, what we do, we take a point F such that AF is equal AB. It's a very simple thing. Take a compass and do, and we get point F. We could do that, right? So then the second thing we do a perpendicular thing from AC toward BC. We put this perpendicular thing, which will intersect our side at point E. Yes? Yes, good. Now we will put this other perpendicular thing. Let us, by the way, see. It's fairly obvious that AB is equal to AF by construction. Right? And it's fairly obvious that AC is perpendicular to EF by construction. This is literally, we don't need to prove anything because that's what we did, that's what we constructed. Now, here we need to do some careful mathematics. First of all, let's observe that the angle CEF, this angle here, is equal to the angle CFE minus the angle of ECF. Why? Because it's, the sum of the angles of a triangle, right? Which is equal to 90 degrees minus 45 degrees. Minus this 40. We know that this is 45 degrees, right? Therefore, this one is 45 degrees. Everybody agrees that if this is 90 by construction, this is 45 because it's diagonal of a square, right? Therefore, this is 45. Everybody agrees, yes? Good. Now, CEF, the angle CEF, is equal angle ECF, implies that these two sides are equal. Because if you have a triangle where two angles are equal, two sides opposite these angles will be equal. It's not a very complicated mathematics, but it is mathematics. Now, it's going to go really complicated. So what we do, we connect F with B. Right? And then we observe following very, very trivial things. We observe that ABC, which happens to be 90 degrees, yes, is equal to AFE, which happens to be 90 degrees, but we don't particularly care, right? So then we know that ABF and AFB, these two angles of the triangle ABF, are equal. Why? Because the triangle is an isosceles triangle, right? Therefore, the angles opposite the equal sides will be equal. So these two angles are equal. Well, which means that these smaller angles here, the angle BFE and the angle EBF, are also equal. Why? Because both of them are equal 90 degrees minus equal angles. And that obviously will give us equal angles. Which means, by the way, if these angles are equal, that means that EF and EB are equal. Do you agree? Yes, because, by the way, they have to invent all these mathematics on the way. You, of course, learned it at school, but they didn't. They wrote the textbook just to prove that. They literally, I claim, developed their mathematics from that construction. So that whatever they needed to prove, they reduced to little lemmas down to axioms. So now what we get is BE is equal EF. Everybody agrees? Okay. Now, what we know is, let me just check if I do it. Yeah, I do it here. We know that FC is equal FE, right? We know that. We proved that because this triangle CFE is an isosceles triangle. So these two are equal. And then we also, just a minute ago, proved that FE is equal BE. Right? Now, we're very close to an amazing discovery. Well, let me do it here. It's easier to do it here. It's a bigger square. We know that AC is measurable in inches, yes? We know that AB is measurable in inches, yes? We know that AF is measurable in inches. Everybody agrees? Yes, but by construction. Then FC is measurable in inches because it's a difference of two things measurable in inches. Right? Now, therefore, FE is measurable in inches, yes? Therefore, EB or BE is measurable in inches. And therefore, final step, EC is measurable in inches because it's the difference, right? So this is absolutely beautiful because we just found a smaller square such that both diagonal and side and diagonal are measurable in inches, right? Contradiction. Why contradiction? Because we agreed that this square is the smallest such square. This is amazing, right? In some sense, if you learn one thing from this course, learn this one. It's just the thing of unbelievable beauty. We sort of start constructing these little triangles, and then we figure out that our algorithm will not stop. By the way, what we proved is the algorithm. Remember the algorithm? This piece of code will not terminate. If you give it AB here and AD there, it will keep going and going and going and going. It will never stop. It will never return an inch of any kind. Because observe, I used inch, but I could use any measure. It will never work. So that, of course, was a terrible, terrible surprise. Because what it meant, they cannot discretize space. And observe, by the way, this is a little thing that we sort of reduce it by more than factor of 2. It's not necessary for our proof. But we didn't just construct a smaller square. We constructed a square which is more than factor of 2 smaller. So we keep shrinking and shrinking and shrinking, forever. Because now we could construct, you realize why forever? Because we could take this square with this diagonal, and we'll keep going and going and going. Wonderful. So what did he discover? That's what we say nowadays. He discovered. But he didn't care about words like that. What he discovered was that there is this fundamental non-terminating procedure. Space cannot be discretized. And it was a shocking discovery. How shocking? it was so shocking that there is this tradition that everybody in the order was sworn to secrecy, not to disclose such a disturbing discovery to the outsiders. Because, the world will collapse. There is a non-terminating, it's like, if you find out that inside Linux there is a non-terminating loop, you better keep your mouth shut. Because otherwise, the entire e-commerce infrastructure would be threatened. Something like that, but deeper. Right? So from their point of view, there was this metaphysical crisis. So as the story goes, there, of course, somebody couldn't keep his mouth shut and disclosed the secret to the unwashed masses. And that was a terrible thing, because basically what he told the unwashed masses is that our guys, they don't really know anything. So it was a very embarrassing. So God was so upset with this disclosure, goes the legend, that when he went for some traveling business from somewhere to another place, the story doesn't tell us, the ship drowned just because of him. So, which tells you that we should never disclose corporate secret. So, I have to bring some useful stuff here. So, it was a revolutionary discovery. So they reacted, of course, in a very constructive and mathematical way. They said, if numbers cannot explain space, then space will explain the numbers. That is, the idea is that instead of viewing integers as the primitive, they would use space as the primitive, right? And therefore, the entire mathematics will be built on geometry, not on number theory, right? And all the constructions will not be what we would call nowadays arithmetic constructions, but geometric construction. Sort of, they build a formal system, sound system with no contradiction, based on geometry and on their very basic fundamental operations, two operations, drawing a line through 2 points and drawing a circle with center in one point and going through another. Just 2 operations. And that gave them confidence that their structure is solid. And it looks it is solid. I mean, so far we haven't found any problems with their construction. Remember I told you it's not the real proof. That is, it's not the proof. It is the real proof, in my opinion. I have absolutely no doubt that's how it was discovered. But it's not the one which history gives us. And there is another amazing thing, that we don't even know if history gives us anything, because there is a proposition 117 in the 10th book of Euclid, which proves exactly this result. I'll show you the proof. But of course, modern scholars says that it wasn't in the original Euclid. The early manuscripts do not contain it. So they threw it out of all the modern editions. So the proof which I show you is very clearly not in Euclid, according to our historians. But of course, it's a very ancient proof. How do we know that it's very ancient? We don't know how it got into some manuscripts of Euclid and when. Some people say as late as Renaissance times. People just said, well, there is a nice proof, we need to stick it into the textbook. We'll just go and stick it at the end of a nice book 10. It sort of seemed to fit there, because it deals with theory of irrational quantities. But we know that it is exactly the proofs which Greeks used from at least early 4th century. Why? Because it's referenced all over the place. For example, Aristotle, when he wants to give an example of a proof which every child knows, he gives an example of the proof which I'll just show you. Not the one which I showed, the one which I will show. So this is this mysterious proof which from proposition 117 in Euclid, which of course is not a proposition 117 in Euclid. So that's the proof which is much more algebraic in nature and number-theoretic in nature than the original proof. That's why I don't believe it was the original proof. But let us go through it step by step. I rewrote it using modern notations because in Euclid it's just reams of words. He didn't have algebraic notation. He had to deal with sort of composed to segment, stuff. So let us assume that we have a rational number, but this is literally, it's just a restatement of Euclid proof with modern notation. Pseudo-Euclid. So assume that m over n square is 2. Let's assume there is some rational number, m over n, such that when you raise it to square, it will give you 2. And let us assume that similar assumption as the previous one, that it is irreducible. Well, if it's not irreducible, you could always get the reducible by just reducing. Let's assume let's come up with a good example. A good example, somebody say, well, it's probably something like 7 over 5. 7 over 5 is an example which was very well known to the Greeks. Right? Plato calls it a rational diameter of the square. It's a very good rational approximation, because 7 square is 49, 5 square is 25. It's about 2, For practical engineering purposes, it is 2. So, just rounding a little bit. So let's assume that it is 7 over 5. So then we know that if, well, I skip this step. I should be much more careful because people always accuse me of jumping steps. Obviously, what it means is m square over n square is equal to. That's the step I missed. Do you agree? I could open parentheses. Then if m square over n square is equal to, what follows that m square is equal to n square. Right? Just multiplying both sides by n square. Then m is an even number. By definition of an even number, what is an even number? It's a number of the form 2 times something. So, well, okay, we need to, okay, I apologize. Small steps. We know that m square is an even number. Therefore, we need to prove that m is an even number. Let us assume that it's an odd number. We know that odd number times odd number will give us an odd number. Therefore, it is an even number. So, there for some other, I know how to prove it. It's all done. So did Euclid. There is this sequence of proofs from about proposition 26 to about proposition 30 in book 9, which is sort of theory of even and odd. And, for example, the sum of odd number of odd numbers is odd. Sum of even numbers of odd numbers is even. Sum of any number of even numbers is even. And many other profound things. And the same for difference. And, the product of odd and odd is odd. Product of odd and even is even. See, we could do it. So we agreed that m is even. Now, if m is even, we just plug this into our formula. Then 2u square, which is m, is equal to n square. We substitute. You see, we take this, on which we agreed, and we plug this in there. We could, You could substitute another wonderful principle of mathematics, it's equational reasoning. You could substitute equals for equals. So we'll just take this equality and plug it in there. So we get 2u squared equal to n squared. Everybody agrees? No doubters? Good. So, and then we could open this parenthesis. So it gets us to 4u squared is equal to 2n squared. Yes? Very, very small baby steps. Then we could reduce it by 2 on both sides, which gets us to u squared is equal n squared. Yes? Which means, again, here I'm jumping, guys. But, I'm doing the same jump as before, which means that n squared is even, which means that n is even. You see, I had to fit on the page also. So n is even. Again, if you remember one mathematical proof ever, remember this one. It's not a bad proof to remember if it's there. It's like sometimes you have to decide what's your desert island proof. And this is as close to your desert island proof as I know, because it's a very, very profound thing. Nowadays, we get sort of, unless it's very complicated, it's not worth knowing. This is not complicated. But it's just a thing of beauty, right? So we proved using a different, so now we have two proofs of the same fact, right? And this is good. It's actually quite common for mathematicians to look for multiple proofs of the same result because it builds confidence. For example, Gauss was very proud of his proof of quadratic reciprocity law, whatever it might be. We'll talk about Gauss later. Therefore, he spent his life coming up with more and more and more proofs of the same thing. Why? Because it's important. So, since he believed that this was an important mathematical fact, he wanted to have multiple proofs. Our confidence increases. We see the relations of the things. Sort of there is this silly idea that mathematicians just start with axioms, they build a proof of something, and then they go on. No, they want to understand the structure. They want to see how you build the dependencies. So here we showed two different proofs of the same mathematical fact, and it is good. So I talked about it. There is no common measure. We cannot come with a unit. You cannot discretize. We have to build this mathematics either with this infinite descent or with building it on geometry. So these are two alternatives. And time again, as we shall see during these journeys, we come back to this decision. Sort of later on, of course, people reconsider. Sort of they say, oh, wonderful, says Descartes. I could now build arithmetical view of geometry. Remember Cartesian coordinates. But now we see, or even by 19th century, people discover there are some problems with real numbers. So they build more and more. I mean, the crisis will never go away because there is fundamental tension between discrete and continuous. Now I have about 10 minutes to give you one of the most, you see, during these journeys, I had to visit different places and tell you about these places. And we got to the place for which my breath goes away. I become breathless and I cannot say how wonderful this place is. It might be the greatest place ever. This is Athens in the 5th century. A small place, roughly speaking, size of Palo Alto in terms of population. But we look at these words, and if let me tell you, each of the words listed in the bullet one should make your heart either beat fast or stop. Because it's just so wonderful. We start, yes, as in marathon. But let us think about marathon. It was a battle. You might have heard there was a battle. It wasn't just a battle. It maybe was the most important battle in human history. You say Alex is exaggerating. Okay, John Stuart Mill, who nobody will accuse of being an emotional guy like me, a hard-headed English sort of pragmatic philosopher, said that for the history of England, the Battle of Marathon is of far greater importance is the Battle of Hastings, 1066, and all of that. So again, there is this remarkable thing. If the battle were lost, we wouldn't be sitting here. There would be nobody discussing triangles or mathematics or philosophy or literature or music. None of that would exist. These battles, I'm not a militaristic guy, but when I think about this battle, my heart stops because everything, it was this little place versus enormous empire. If you look, they were fighting Persian Empire. They were fighting this. The name of the king was Darius. I mean, he just conquered Egypt. He conquered the world. He was the ruler of the world. His army was in hundreds of thousands. Athenians could field about 10,000 men. That's all they could put, because that's all they got. And it wasn't they had a professional. They didn't have a professional army. It was a bunch of honest farmers putting on their, armament and charging. They really charged. They used this, again, when I look at this list, every name, every place. So what happens? They form a phalanx, the Greek formation. And then they realize if they do what Greeks always do, which is slowly march in formation, they're going to die. Because Persians have these wonderful things called arrows, bows and arrows. And if you slowly march toward an enormous army, equipped with bows and arrows and darts, you're going to die. So what do? They run. They run at huge speed for about 1 kilometer, right? And they charge through the Persian army, the unstoppable, in formation. And that's why we're sitting here, because they were able to charge in full heavy armament for 1 kilometer, facing overwhelming odds. So Miltiades was a great hero. Miltiades, I should have put him there. He was the commander, a great, great commander. How was he rewarded by Athenians, by the way? Anybody knows?
As exiled, he ended up in Persia.
No, that would be nice. No, he was put in jail and basically starved to death. Yes. Okay? So he wins the battle in 490 BC, yes? That's the Battle of Marathon. There was 250th anniversary 2 years ago. The Greece issued a stamp. You should get me one.
I think there are two accounts actually. I think according to one account actually he's exiled.
Right. First it starts with exile. Then he is arrested and starts and died in 489 BC, 1 year after winning the most important battle in the history of the world. That's democracy for you. So, but I mean, when you go away, which you shall eventually, in an hour and a half, Google Miltiades' helmet. Why? Because they actually dug it out. This is this amazing thing. It's again one of the miracles of history. This is the guy who wins the most important battle ever fought. One of the 4 great battles in European history, in my opinion. And what does he do? What would you do if you were this winning general? Well, you're not as dramatic as in ancient Greek war. He takes his helmet, in which he just won this battle, and sends it to Olympia, to the great temple of Zeus, as his offering. And then they dig the dirt at Olympia, and they found the helmet. How do we know it's his helmet? Oh, it says right there on the edge, you could see the picture, Miltiades. It was his helmet. So the fact that we have the helmet of the guy who, I think, isn't it wonderful? I think it is wonderful. So Salamis, another great battle. Yeah, because Persians wouldn't stop. So Darius dies. So his son, Xerxes is named after him. No, I'm joking. Xerxes. He needs to punish those Athenian upstarts. So he assembles an enormous army. Millions, they say. And I believe it. I mean, he's the emperor of the world. Why not? And he marches. This is 10 years after. Right? 480. Right? He marches. All of you heard of Leonidas and Spartans stopping them for 3 days. They just stopped them for 3 days. Then comes this great event. First of all, Athenians are prepared to sacrifice their city. Every Athenian packs his bags, takes his children, and then they evacuate entire city. They move to Salamis, the island opposite Athens. All of them, they abandon everything. Acropolis, the great temples, right? And I wasn't planning to tell you this story, but I couldn't stop. So they go there. They have nothing. And the huge Persian army marches into Athens, burns everything, burns the temples, out of spite. They're not Persians in general, are quite tolerant of other religions. Remember, they were the ones who allowed Jews to come back and start rebuilding the temple. They're tolerant guys, civilized. They just want to rule the world. You know, free trade. They were into free trade. So they conquer Athens, burn it. And then Xerxes, the king, puts his royal throne on top of the Acropolis, sits there, and he's watching this great naval battle. He's going to see his fleet destroy this Athenian and their allies' fleet, and that will be the end. Sort of, for him, it's a big spectacle. He really views it as a performance of the lifetime. It's really happened, guys. So he sits there watching the thing. And there is this amazing battle led by another Greek hero. I did put him there, Themistocles. And Persian fleet is utterly decimated because it's much larger, it's much more powerful. But Greeks realize that if they fight in the straits, Persians will not be able to maneuver. Themistocles is very clever. They destroy the fleet. Civilization is saved. The guy up there on the throne has to pack his bags and run all the way back to Persepolis in Persia. Again, it takes another year of more pipe operations and one more great battle of Plataea to fully handle this Persian threat. But Greeks never forgot. So 130 years later, whatever it is, 140 years later, when Alexander conquers Persia, he burns Persepolis. Why? To pay for what they did to Athens. Because Athens is so wonderful. Again, go, here I got to the list. I'll let you go and we'll come back in 10 minutes.